This is the third part of lecture 8 on fading, diversity, and coding. In the first part of this lecture, I talked about effects of fading. In the second part, I talked about diversity combining techniques to counteract the harmful effects of fading. And in the third part, I'm talking very briefly about space-time coding and the multiple input, multiple output antennas, which are the latest technologies in this field. To start that, basically the terminologies that people are using around, one is SISO, we had it before. Actually, we had the 802.11 SISO model earlier in one of our homeworks or whatever. It's single input, single output, one transmitted antenna, one received antenna. And then you have SIMO, single input, multiple output, and you have MIMO, which is multiple input, multiple output. So basically, you can have multiple M antenna elements at your base station, for example, and you may have one at the terminal. Then this would be like a SIMO, one against multiples. If you have multiple here, multiple in here, is MIMO. If you have one in here and one in here, it's a SISO. That's the basic terminology. Now, why is like multiple antennas so important? I think I described it in section 8.2, and I told you that this is the focal point for radio design. While for the voice band modem, the focal point was like increasing the number of points in the constellation using trellis code. And regular codes are not even good for voice band modem. Nobody uses coding in voice band modems because you lose the bandwidth. The only bandwidth efficient coding is trellis code modulation, which is used in voice band modems. So the stories in the radio is different, but why it is different? Because we are fading. And as soon as we are fading, now coding becomes very important for the reasons that coding is actually time diversity, provides time diversity, okay, in a sense. Now, so to start the story of this part, we go back to the same thing that we had a little bit earlier, is the issue of maximum ratio combining. If I have one transmitter antenna and I have two receiver antenna, this structure is the same as the same structure that I showed you earlier. Both of them are coming from this paper by Alamouti, a simple transmission technique for wireless communication. Actually, this is the first paper and the simplest code for the so-called space-time coding, which was introduced in 1998. And then the person who did it, Alamouti, he was at ComDisco. They are designing like another version of MATLAB. ComDisco was like a block diagram oriented simulation model for radio channel. And so I believe he was one of the sales managers there, and he was doing all different like combinations to show the people, and he comes up anyways in his interactions with the Bell Lab people, he comes up with this simple scheme which is very helpful, and then later on at Bell Lab people build up on top of that a lot more. But still, that simple code is the most popular and is the one that some of the standards are considering. But it has been one of the hottest topics in information theory in the more recent time. Information theory, everything happens every like 10, 20 years. The one before that, very important, was possibly OFDM, and before that was trellis code modulation. And before that was QAM. So QAM was 1970, trellis code modulation 1980, OFDM, let's say 1990, and then you're talking about like space-time coding in 2000. And in 60s, it was like adaptive equalizer. So every 10 years, they have like a new technology coming, which just changes this stuff. But anyways, what is the idea? The basic thing is, this is a simple maximum ratio combiner. We saw that earlier. And I have one transmitter antenna, two received antenna, and all set. No problem. But what is the problem with implementation of this? When my receiver is the mobile, it's difficult to have two independent antennas. So how you want to remedy that situation? That's how space-time coding starts. This fellow Alamouti comes with a very simple, in fact, solution in here. The simple solution that he has is that rather than having two antennas at the receiver, you have two antennas at the transmitter. At this base station, I can easily have two antennas. Then the symbols that you want to send, you send symbol S0 in here, and then S1. In the other branch, you send S1 and S0. Remember, all the maximum ratio combiners that we had so far, the transmitter was sending the same symbol. Okay? And there was no repetition. And then the receivers received the same symbol. In here, transmitter actually, and even if you wanted to have the same thing, maximum ratio combiner, you could have two antennas at the transmitter, and each of those antennas, they send the same S0, and one antenna and receiver receives that. But that would be equal gain combiner, not maximum ratio combiner. Do you follow me? See, in here I have a maximum ratio combiner, two antennas as receiver. Okay? It's difficult to be implemented. I send one symbol, I receive two versions of that symbol, I add them up together. That's where I am. The second one in here is this. But before I go there, I can tell you this. I can have another system. What is my incentive for having two antennas at transmitter, one at the receiver, because one is base station, I can have two antennas, and one is the receiver. But if I have two of them like this, I mean I have two transmitter antenna, this one and this one, I can send S0 in here, S0 in here. Then at the receiver, what I receive is S0 times H1 plus S0 times H0. Do you follow me? What is this? This is equal gain combiner. I had two transmitter antenna. I have one receiver antenna. I cannot adjust anything. I receive both of them on top of one another. When I receive both of them on top of one another, they just add with equal weight. So it's an equal gain combiner. What is the problem with equal gain combiner? It's not optimal. Okay? Now, what this guy comes, I mean the scheme that this guy comes with is that I'm not sending the same signal from the two antennas. I send different antenna, different signal from them. That's the new. That's where the time is get mixed with a space. Okay? Up to now, everything was what? A space. Diversity. Now, time comes to the picture. So, these are time slots. In time slot number 1, I send S0 in here, S1 in here. In time slot, next time slot, I send S1 in here, S0 in here. And then when I receive them at the receiver, this is the channel, this is the channel, similar to what I had in the past. So I have, at the receiver, I have two time slots. This is the time slot T, if you want first time slot, second time slot. First time slot associated to that, I get this. Second time slot associated to that, I get this. Okay? Then he gives you some processing thing in here. I estimate the channel, first channel, second channel, and I multiply them with the top one, and then I end up with this things. The first one is this. The second one is this. If you remember, I mean, if I process them with the method that he's prescribing, which multiplying with these matrices. The first sample, Z0 and the Z1, for the decision. Two variables that I create at time 2t. If I create them from this one and this one, according to this matrix multiplication, I end up with these things at the output. And if you look at these output, this one is like symbol A0 multiplied with this. This is very similar to the output of maximum ratio combiner that I had earlier. Earlier, where did I have it? Maximum ratio combiner in here. You remember? At the output of maximum ratio combiner, I had this thing. The symbol multiplied with alpha1 square, alpha0 square times ES plus noise. Okay? Do you remember that? This is the output of maximum ratio combiner with one transmit antenna, two receive antenna. Now, what he does in his stuff in here, the output is exactly the same thing. But the processing is different. And it's only an algebraic manipulation in there. Okay? But what is the difference between this one and the one that I showed you earlier? In here, you have created a maximum ratio combiner with two transmit antenna. The other one was maximum ratio combiner with two received antenna. In order to make this thing happen, you have shuffled the signals at the transmitter antennas. So in addition to space, you have time diversity there. Okay? So it's called a space-time coding. This is the simplest one, and it gives you the simple idea. Now you can get this, and based on that, build up more complex things. But did you understand this simple one? So what has happened in here is that normally I was sending one S0 and I was receiving through H1 and H0. I was receiving like S0 times H1 and S0 times H0 and H1. And then I was multiplying that with these squares and add them up. That was maximum ratio combiner. In here, I'm sending two symbols in two time slots, and then I process them very simply with this matrix in here, and I end up with the same answers. But I send two symbols. After two symbols, I decide on both of them. Okay? When I want to send the symbols, I shuffle them. I send one from here, the other one from the other one from here, the other one from the other. And this is the basic idea of, and that's actually, this is the most popular as well. The simple and the most popular. Then people thought that, okay, now that I have this simple coding and shuffling, why not I use more complex things like trellis code modulation, for example, or other formats. A lot of research between 1997 and up to even now. Variety of format for space-time coding has been studied, but yet still none of them have shown a lot more superiority over this. Okay. And still this is the most popular one. Then in the same paper, he goes also and gives you matrices for 2 by 2. If you have two transmit antenna, two received antenna, how to decode them. If you have again a space, you have added the time elements. Okay, how to encode them. So what are the issues in here? One is the issue of encoding. When I'm sending this stream of data, which is coming S0, S1, how do I distribute them between two antennas? Okay. The other one is, what should be my matrix at the receiver to process them? Okay. And people go over that for variety. And they change, if I change the number of transmitted antenna and number of received antennas. Okay? So I went over the detail of what simple Alamouti is called for 2 to 1. Okay? The rest, this is for 2 by 2. These are the equations, again given by Alamouti. a lot of algebraic calculation, but it's simple. It's addition and subtractions, etc. Very simple codes. Okay. Now the next issue which comes is, what is the effectiveness of this? How does it compare? And what he does, these are the things that these are very, very interesting results. If you look in here, this one, he has done the simulation. Okay. This one is one transmit antenna, one receive antenna. You want to compare this, you come back with our previous things. That's this. That's this curve. Okay. But this is calculation. He has simulated that. Okay. You follow that. This is performance over a fading channel only. That's what he has in here. This is performance over the fading channel. One transmit antenna, one received antenna, and the channel is really fading. The second one that he has in here is maximum ratio combiner. One transmit antenna, two receive antenna. That's this one. And then he has one transmit, four received antenna, maximum ratio combiner. That's the square one, which is in here. This curve, and this curve, okay, these three are equivalent to the three curves that I had in here. This one, and this one. Okay? This is the standard maximum ratio combiner. Means that I have one transmit antenna, two independent received, and four independent received antenna. They are very, very equivalent to this tree. Now, but the important one are two new ones. Two new ones, this is his new scheme. Two transmit, one receive, two transmit, two receive. This is two, this one, the diamond. Which one is the diamond now? Finding the diamond. Two transmit, one receive. I think this is this one. And then two transmit, two receive. That's this one. So what you see is that with this coding scheme that he's suggesting, with two transmit and one receive antenna, you have a performance which is, mine always, my interest was what? 10 to the minus 5. With one, I was around 45. Do you remember? That's the same curve. But these are simulation. Okay, in here I had around like what? Around 25. In here I had around, I mean in his case he has around like 10 dB. This is a little bit, oh, this is very positive, very good. Now what happens is that when I switch from two, in here is one transmit, two receive. This is two transmit, one receive. This is one transmit, two receive. The difference between these two is around like a couple of dB. If you come in here, this is one transmit, four receive. This is two transmit, two receive. Okay, the difference is again like a couple of dBs. It's perfect. Okay, but physically, what is the difference, and how does it entangle with my previous discussions? I told you, implementation of four antennas in a like a small like handset like this is impossible. First of all, the space is not enough, and if you put four antennas, how do you want to talk? You are going to blind your eye. Too many antennas around. But anyways, this is the value of the work. Okay, and it's very simple, very straightforward. What are the other variations? People started immediately after his work, or actually concurrent with that. Kalderbang, Vahid Tarouk. Actually, Vahid Tarouk is coming to give a lecture in WPI on September 13. He's at Harvard now. Those are the guys who took this idea, basic idea, and actually they were working with him, and they are published together. But they went to more complex structures. One of them is just using trellis code modulation. You remember trellis code modulation is the one that I told you they used in voice band modems in early 1980s to go above 9600 bit per second. Okay. Now, what is the advantage of trellis code modulation? It's not regular coding. Within the same bandwidth, it improves the signal-to-noise ratio requirement. Okay. So your data rate remains constant, but your performance improves. So it's good for band-limited channels. But anyways, they have tried to apply that to what? Trellis code modulation. To apply the trellis code modulation to multiple antennas. So I have two antennas, and I take the codes and I divide them, and then at the receiver I have a very complex receiver for that. That's one type of thing that people went after and did a lot of research in that. The result of the performance of these guys, there are some performance results, but, and this is the paper for that performance. And another thing that they did, the result of Alamouti was what? Related to, these results are related to narrowband communications. Means flat fading. You have only one path in the channel. Now the question is that if you have multipath, what will happen? And actually effectiveness of this kind becomes lower. But still people are working on that. But anyways, for these more complex versions, trellis code modulation version, now if you have multipath, you can take care of multipath a little bit more effectively. But receivers, they become more complex. These are some performance results, more recent ones. Then, while they were working on these things, another thing which come in parallel to that, which is good to know about it, is the so-called V-blast and D-blast, which are two methods of coding, encoding of this thing. In order to go there, before that, let me just remind you this thing. You have basically this, like, let's say, one example, which is coming from this particular paper. You have 3 transmitted antenna, 3 received antenna. You have a bunch of bits coming in, a stream of bits. You have to first divide them to send one part to antenna 1, one part to antenna 2, one part. And then these are the signal constellation of each of these streams. Then at the receiver receives something like that. And then you process them to get these things back. Okay? And then you have these data coming out. You put them back together, and this is the data stream which goes out. Okay? Now, in the MIMO type of application, these information which goes to each of these antennas are different. Okay? But in a standard like antenna system, before this recent MIMO, these information were the same. Okay? Now, this is like 2 famous ones. D-blast, Bell Laboratory space-time coded diagonal, and Bell Laboratory space-time coded vertical. Okay, these are 2 coding schemes that were introduced by Bell Laboratory. Very complex coding and decoding technique, which is an advancement to Alamouti's code. Okay, basic difference between them basically is in the format that they put in the diagonal way. They take the information symbols like B1, B2, B3, B4. They repeat it in here. But they are repeated similar to Alamouti, means that there is a delay between them. So that's why they call it diagonal. Okay, first one starts B1 in here. The second one, B1 starts in here. Third one, B1 starts in here. But then they repeat these things. Okay, very similar to Alamouti. Alamouti was 2, and this is like 3 of them. But it looks like that's D-blast. The second one is vertical. In here they have B1, B2, B3, B4, B5, B6, So basically what they are doing, they are talking about variety of coding. Like early days of coding, people were looking in block codes, convolutional codes to see that what will happen. Now they are doing exactly the same thing, but over fading channels and over fading multipath channels, both of them. Okay, flat fading and multipath fading channels. The hope for all of these guys was like this type of thing. These are some bounds. In here you have capacity bits per hertz. For example, capacity of binary PSK was what? 1 bit per hertz. If you go 64 QAM, for example, is 6 bits per hertz. Okay? Now, with the MIMO over the radio channels, you can have, for high signal to noise ratios like 35 to 40 dB, you can have up to 70 bits per symbol. So very high capacity. And in radio channel, it's very, very important. Why? Because bandwidth is always scarce. So people were doing a lot of actually research. It was like a revolutionary idea in late 1990s up to even right now. A lot of PhDs, a lot of research around it. But it cooled down more recently for several reasons. Number one is that 3G was not very successful commercially. So people, they're thinking about this as next generation, MIMO for the 4th generation. So people got cooled down for the 4th generation. And the importance of wireless LANs and WPANs started to overshadow this thing. So people are more moving to those areas more recently. And the other thing was that the Alamouti's code, as I told you, is for flat fading channels. And all of these complex codes after that, a lot of these analysis and these bonds are over flat fading. When you go over multipath fading, the receivers becomes complex, and also the performance is not as good as non-multipath fading environment. This is another actually one of those. This is VBLAST versus DBLAST performance. With VBLAST, DBLAST coding, they are talking about something like 8 and 7 for signal to noise ratios around 30. They are talking about 7 to 8 bits per second per hertz. I mean, if you want to compare it with these bounds that were around 30, for the bounds we had like 60. So means that you have still plenty of way to go. And I think with that brief introduction, if I want to summarize space-time coding, the new idea which comes to the picture is that different antennas, they are using different codes. So that's the time difference. And then the value of this thing is for the time in practice, for the time that you have multiple transmitter antennas and like maybe single or double receiver antennas. Number 3 is that there has been significant amount of research in this area recently, and the hopes for this thing was that this can be a potential revolution to increase the capacity of cellular networks. What, however, has been left is still the MIMO. People are trying to apply the MIMO for wireless LANs. They are trying to apply MIMO for CDMA systems. So MIMO, not only up to here we were talking about like in narrow band, means like flat fading channels, but if you go to multipath fading channels, it is effective too. So when I'm discussing in my next 2 lectures, when I'm discussing wideband modems, I will show you some results related to effectiveness of MIMO and space-time coding in multipath fading channels, not in flat fading channels. Means that the channel is modeled with more than one tap. That's multipath fading, and then, or frequency selective multipath fading. And then if the channel is modeled only with one tap, that's flat fading. What I showed you in here, the result of Alamouti was flat fading. And with that, I can close this lecture if you don't have any questions.